SwayamPrabha. Digital India. Educated India.
Hello all. In this video we will be looking at one more way of characterizing polymers, where we will discuss about this time temperature superposition principle. Essentially it says that both time and temperature have an equivalence between them, which means you can use one as a trade off for the other, where for some of the experiments cannot be done, let us say for very long times or very short times. This is a very powerful tool, especially if we are looking at how to design or how to know how the polymer behaves after, let us say 10 or 20 years. So, let us say we have used this polymer, let us say for a solar panel or some other structural applications. We know that most of the structural applications do last for few decades, like 10, 20 or even more times. So, the question now is, as a designer today, if I need to choose a polymer which is structurally good even after a few decades, how do I choose that polymer? So, which means I need to either know the mechanical properties, how they change after 20 years, or I should be able to predict what happens after 20 years. But I think all of us appreciate that either we do not have data where people have tested for 10 or 20 years and then that data is available for us so that we can make our design decisions. Even if there is a data like that, probably it is only limited to very few materials, like 1 or 2 materials. But as a designer, you will be looking at different materials and you need to have a tool with you where you can say how can I predict the material behavior after few decades. So, we will see that this time temperature superposition principle will be handy in those scenarios, where you can do a test for a reasonable amount of time, like within a day, and use that data to extrapolate how the material will behave for very long periods of time, like an year or a decade or more. Okay. So, let us get started with here we will first identify what is the equivalence we have between the time and temperature. So, I will be again using the information we discussed in the previous video, where we discussed about the DMA and DMTA, which are the dynamic mechanical analysis as well as the dynamic mechanical thermal analysis. So, if you recall, the plot here is for Maxwell model. We are looking at, once we do a frequency sweep, meaning if you start with low frequencies and increase the frequencies to very high frequencies, we have shown through equations how we can see the storage modulus varies with frequency. We have also shown it for loss modulus and tan delta, but let us focus on the storage modulus. So, we see at very low frequencies it has a very negligible value, but around close to your relaxation times there is a steep increase in the storage modulus, and at very high frequencies again these modulus values are high, right. So, the same data we are showing here where the x axis is different. So, earlier it is frequency, now it is 1 by frequency. So, in the previous lecture as well we mentioned this, saying that 1 by frequency gives you a sense of time. So, which means as you increase the time at low times, or if your tests are done slow, then your modulus is high. So, actually these are 1 by frequency is low. What it means is it is a sudden test, because the time available is less. So, it is almost like if you are doing a tension test, we are either in tension or compression, either stretching or compressing very quickly. So, there is less time to deform. From our molecular structure discussions, we know if we are loading anything strong, the chains have a more resistance to deformation because you are not giving it enough time to relax and then accommodate your deformation. So, mostly the modulus values are high, but as you increase these times and where it reaches the relaxation time, which in this case is 15 seconds, that is when it goes from very high modulus values to very low modulus values. So, which means again at very high values of this 1 by frequency, or otherwise we are talking about a very slow test where you give enough time for it to deform, then again the modulus values are low. Okay. So, we have only shown that between frequency and 1 by frequency the trend of the curve changes. In the last class we have also seen this, this is the storage modulus. Again, if you notice, now if we increase the temperature going from a low value to a high value of temperatures, then initially at low temperatures the modulus values is high, because we know mostly these polymers are in a glassy state below the glass transition temperature or below these relaxation times. But beyond this glass transition temperature, again the modulus values are low. Okay. So, what we are trying to show is, if you especially focus on this let us say the second figure and the third figure, we see the trend of the modulus is similar. So, where it starts with a very high value and then it suddenly decreases to a very low value, which is again constant in both these figures 2 and 3. But here we have seen in figure 2 it is related to the time, and in figure 3 it is related to the temperature. What we are simply trying to show here is both time and temperature, they bring the same kind of changes in the behavior of the polymers. Now, so this is what we call it as the equivalence, but how do we take advantage of these equivalence is what we will discuss in the time temperature superposition principle. Okay. So, here we are looking at compliance and the x axis is time. So, at several different temperatures we have seen how the compliance values changes with time. So, these are simply like our relaxation test or the creep test. Here it is a creep test, meaning if you apply a dead, one end of the specimen is fixed and the other end if you apply a dead load, we know that initially there will be a sudden change, but if you give enough time the elongation keeps on increasing, which means the creep compliance continues to increase with time. That is what we are seeing here, saying that these brown marks correspond to 130 degrees. So, if we are doing this test starting from, so which means you do a creep test and measure the creep compliance, after here the units are minutes and this value, the minimum value we have seen is 30 minutes. And the maximum value we are conducting this test is for 600 minutes. So, which means from half an hour to 10 hours within a day. So, these are the different values of compliance you got when you have tested these at high temperature of 130. But now once you decrease the temperature, of course again these compliance values decrease. So, here is the data showing from the lowest temperature is 90 and the highest is 130, all in degrees centigrade. Okay. So, as you can see, these are experiments we have conducted, and these experiments showed that are done between within 10 hours. Now, the question is, how can we use this data to predict how this polymer behaves at very long times? Long times meaning we want to use this data to predict how this polymer behaves after a week, after a month, after a year, and maybe few decades. So, what this superposition principle says is, individually let us say if we want to develop a curve, let us say for example at this temperature, the second temperature is at 125 degrees centigrade. which means we will not move this curve at 125, but the other curves we move either to the right or left, such that all these curves fall into one single curve. So, for example, this 130 curve I should be moving to the right. So, if I move to the right, then it will take some shape like this, right. And similarly, this curve, the third curve in red, is at 122 degrees centigrade. This should be shifted to the left, because we are saying if this is the T reference, means reference temperature. So, this curve should be moved to the right, 130 curve should be moved to the right, and 122 curve should move to the left, then you get some curve. If you continue to move the rest of the curves accordingly, you will get one single curve which looks something like this. So, bear in mind, here I have taken the T reference as 110 degrees centigrade, meaning this 110 degrees centigrade curve is in green. So, these data we have not moved, but the all other data either they are moved to the left or the right. Now, let us see what are the curves we move to the right. We move the curves which are tested at above the reference temperature. So, like this 130 curve, 125, this red is 122 and the blue is at 115. All these 4 curves we shifted to the right, such that there is a continuous curve we can see, and the other curves which are at 90 degree centigrade and the 100 degree centigrade curves we shifted to the left of this 110 reference curve. So, what we see is a continuous curve which we now call it as a master curve, meaning this curve gives how the compliance of this particular material varies at 110 degrees centigrade. Now, let us see what this signifies. So, bear in mind the x axis is in log scale. So, what it means is 10 power 4 minutes is close to 1 week, and 10 power 6 minutes is close to 2 years, and 10 power 8 corresponds to 200 years. And similarly, if you go to the left, at least we in this plot we have shown till 10 power 0, which is 1 minute. In fact, the data can be also be taken less than 1 minute, but let us limit it. So, what is it we are showing? We are showing at 110 degrees centigrade how the compliance varies from 1 minute to 200 years. This is what the master curve does. But now let us say instead of 110 degrees you want to know how this polymer behaves, let us say at a higher temperature 125 degrees centigrade. So, let us say at 125 degrees centigrade you want to know how the polymer behaves. Again you are interested in the large time scales. So, how do we do? So, since we have one master curve, we can use that master curve and either shift left or right. We shift left at increasing temperatures and shift right if your temperatures are low. So, here I think we already shown, let us say this is the master curve at 125 degrees centigrade. How did we get this master curve at 125? Once we get a master curve at 110, I can shift that curve to the left. This is called as curve shifting, and we will later see what is the theory behind this time temperature superposition principle, and using few equation how can we make these shifts. But I would appreciate or I hope you can appreciate the importance of these curves. We started with testing at different temperatures in a limited time. So, for example, between 30 minutes and 600 minutes, and using these data we are able to extrapolate or find how this polymer behaves across a wide range of time scales, starting from 1 minute to let us say 200 years. Okay. So, now let us focus on this shift factor. We said once we have one master curve, we can get to the other master curve by doing a shift. That shift is denoted by this AT, which we call it as also the shift factor. So, let me show you what it means. Let us say again we are talking about y axis is the compliance and x axis is the time, but bear in mind we will be focusing on log scale. So, it is log time. So, let us say this is the creep compliance at a reference temperature. So, let us say this is a time t reference, and this corresponds to a relaxation time or the retardation time log t ref. Relaxation time log tau ref, where tau ref is the relaxation time corresponding to the reference temperature. Now, once we change the temperature, this curve will either shift to the left or right. Let us say this is the curve at a different temperature. And let us say this has a relaxation time tau, and this, as I mentioned, is corresponding to this new temperature T. Okay. So, this shift factor is this difference log AT. So, how did we get this? So, we said log of tau is given as log AT plus log tau reference or the relaxation time at the reference temperature. So, if we remove the logs, one should be able to write this as tau is equal to AT times tau reference, or AT is simply the relaxation time at temperature T divided by the relaxation time at temperature T ref. Okay. Now, let us see the basis by which the theory which allows the time temperature superposition principle. So, it is based on this kinetic theory of polymers, which was initially developed for dilute solutions, but this is developed again only for temperatures above Tg, meaning that the time temperature superposition whatever we have seen is only applicable for temperatures above Tg theoretically. But later from dilute solution it has been extended also to rubbery polymers. Again I should specify that these are all above Tg as per the theory kinetic theory of polymers. So, essentially what the kinetic theory of polymers gives you is, it is able to give you a relation between your relaxation times tau with temperatures T naught and T. T naught is the reference temperature and T is the new temperature. Here as written here, tau is the relaxation time at temperature T, this is the viscosity and rho is for density. Essentially like we said this shift factor AT is nothing but tau by tau naught. So, this is the relaxation time relaxation at temperature T by relaxation at temperature T naught is given in terms of this viscosity term, density term and the temperature terms. So, this is what the kinetic theory of polymers gives us. There is one other important point I need to mention, saying that we assume this polymer is thermorheologically simple, but let me explain what it means. It means that previously we have shown that any polymer, it is not like it only has one single relaxation time. Actually in real polymers it has several relaxation times, because even within a single chain every segment of the chain will have its own relaxation times. So, what we are trying to say is all these relaxation times within a polymer will follow the same shifting factor. So, no matter let us say this particular polymer has 10 relaxation times, all those 10 relaxation times needs to be shifted equally. If we are able to shift it equally, then we should be able to say the polymer we are working with is a thermorheologically simple polymer. This is useful because by this assumption we can shift the complete curve, otherwise what will happen, we have to shift only a part of the curve step by step. So, you need multiple shift factors for a single curve, but because of this assumption for a complete curve we only have one shift factor, and once we move it we get the master curve at a different temperature. Okay, this is what is given by the kinetic theory of polymers, but again I have to repeat that both the time temperature superposition principle and the kinetic theory of polymers by which it is based on, both of them are strictly valid above Tg. But in practicality people found that the time temperature superposition can also be used slightly below the Tg, and how far away from the Tg it is not clear. It all depends on the polymer you are working on, but the rule of the thumb is if you are able to shift these curves and then get a continuous curve, you can still apply the TTSP or the time temperature superposition principle. But now let us see, there are two expressions we will be looking at to find AT values. First is the WLF equation. In the literature of polymers this is a very commonly used equation, and this is very popular because it is very handy. You can simply pick a polymer and find your AT values very quickly. WLF is actually an acronym for three scientists, William, Landell and Ferry. So, it is again based on a free volume of a liquid, based on the theory of free volume of a liquid, and again like the previous kinetic theory and the TTSP, it is only valid above Tg. Okay. And log AT is given in terms of these constant C1 and C2 and then your two temperatures, the new temperature and the reference temperature. Tr is the reference temperature. The beauty about this expression is it is an empirical expression. What these three scientists have done is they have taken lots of polymers, tested it, and then after testing they have fitted a curve which gives you a C1 and C2 values. So, the C1 and C2 values are constant, or C1 is 17.44 and C2 is 51.6, and this you can apply only if your reference temperature is Tg. So, this is an important condition, saying that if you take the reference temperature same as the glass transition temperature, then you can use these values of C1 and C2. So, as you can see, this equation is very powerful because you do not need to know much about the polymer. You got this value of AT simply by knowing the two temperatures, the reference glass transition temperature of the polymer and your operating temperature. But though initially it was very popular, later people realized that There are few polymers which slightly vary, meaning the C1 and C2 values does not exactly fit in, but still people use it because it is like an initial approximation to how the polymer behaves. So, before we move to the next slide, so we mentioned that again this WLF is only valid above the glass transition temperature. So, but if we want to use this or find this value of 80 for temperatures below the glass transition, that is when we use a second equation, which is the Arrhenius activation energy equation. So, perhaps most of you have heard about this Arrhenius equation. It is an equation which is mostly used in kinetics. So, it tells about how fast a reaction happens, and this is captured through this equation, which is called the Arrhenius activation energy equation. So, the left hand side you are seeing the relaxation time is written in terms of this constant A. EA is the activation energy and R is the gas constant, T is the temperature we are working at. So, from this let us see how we should be able to find the value of 80. So, for this if I take log on both sides, it will be log relaxation time will be log A minus EA by RT, and log of E is 1. So, it is a constant. Now, let us introduce AT. So, log AT is log tau by tau reference, which can be written as log tau minus log tau reference. And once we use this expression and substitute it, this we should be, because log A will be the same both for the tau and tau reference, they both cancel out. We will be left with the second term where the constants are EA by R. From the log tau we get this minus 1 by T, and log tau R we get 1 by TR. So, now we can write this log AT equals EA by R 1 by TR minus 1 by T. Now, if I write this in terms of log base 10, then the final expression will have this. So, this constant 2.3 is coming because we are now writing in terms of this log base 10. So, this is the equation we use to find the value of AT. As you can see, the quantities we need to know to calculate these are your activation energy EA, the gas constant R, and the temperatures T and T reference. So, once we know this, we should be able to find the value of AT. But let us talk a bit about the applicability of this equation. So, previously we said WLF equation is strictly valid above Tg, but Arrhenius equation does not have any of those restrictions, meaning this can be also used below Tg. So, in practice actually for temperatures above Tg people use the WLF equation, and for temperatures below Tg people use the Arrhenius equation. So, again to recap, why are we studying about this AT? Because once we know the shift factor and we also know a master curve at one reference temperature. So, now with this shift factor I should be able to get a master curve at a new temperature T. So, in summary, what did we discuss in this video? We started by saying both time and temperature have an equivalence, meaning both time and temperature can be traded off for our requirements. So, let us say if we are looking for the long term behavior of the polymers, we said since we are not able to wait for long times, we will work with temperatures to be able to predict the behavior at very long times. Actually, we can use the same for very short times. So, for example, if we want to know how the polymer behaves at less than a second. So, it is very hard to design an instrument where you can really capture the behavior in a fraction of a second. But then again, using this time temperature superposition, we can shift it to low times, meaning you will do the tests in the order of minutes like we showed in this video. But again, using that data, you can shift it to very low times and see or predict how the polymer behaves. So, it is not always that we use this to predict how the polymer behaves in long times, but we also use it in very short times or very high strain rate events. So, we said these shift factor equations. First we discussed with the kinetic theory of polymers. This is the theory on which the time temperature superposition principle is based on, and we also have shown or discussed that both of these are valid above Tg. But to get an equation for this shift factor At, we use the WLF equations for temperatures above Tg, and we use the Arrhenius activation energy equation for temperatures less than Tg. So, this video we have tried to show you how to characterize the polymers and how to take advantage of these equivalence between time and temperatures, so that we can use the limited data and extend it for either different temperatures or different time scales. Thank you.